A very good morning to all of you. We will continue with our discussion in magnetostatics. Let us recall in the last lecture we had looked at effects of magnetic field on moving charges. So, we had calculated the trajectories of particles, charged particles as they move in the presence of magnetic fields and electric fields, and we had used, you have seen some applications of this in the discovery of the electron by J. Thomson, then applications in mass spectrometry and also in particle accelerators like the cyclotron. So, all the discussion was based on the effects of magnetic force and electric force on moving charges. Now, today what I want to discuss is the effects of magnetic forces on current carrying conductors. So, let us begin our discussions. So, we have what we want to discuss is force on a current carrying conductor. So, remember when a wire is carrying current, these are actually charges moving in the wire, primarily electrons moving in the wire from one direction to one position to another position, that constitutes the current. But conventionally we define the current as the direction opposite to the electron flow, and so the current is actually nothing but flow of electrons through a wire. So, electrons are propagating through the wire, charged particles are propagating through a wire. Now, when you place this wire in a magnetic field, we have seen that there is a Lorentz force acting on each of these charges. So, when the wire is placed in a magnetic field, the magnetic field will have a force on each of these charges, which then transfers itself into the wire, and the wire gets pulled or repelled because of the presence of the magnetic field. So, magnetic forces on the charges have finally an effect on current carrying conductors. So, our objective is to find out what is the force acting on a current carrying conductor. So, for this let me assume that we have a long straight wire of cross sectional area A of length L carrying a current in this direction. Now, for the moment I will assume that the current consists of positive charges moving up, and I will show you later on that the force that we calculate will be the same as if the electrons were flowing down or the positive charges are flowing up, it is the same. So, I take a length L of the wire and place it in a magnetic field which is pointing into the plane of the paper, which I draw through crosses. Now, what this implies is now the current is flowing in the upward direction. So, if I assume that the current is produced by positive charges, each of these positive charges moving up. So, when a positive charge is moving up in the presence of a magnetic field pointing downward, we know that there is a Lorentz force acting on this, and that force is q v cross b. So, if q is the charge and v is the velocity of the particle and b is the magnetic field, the force is q v cross b. So, v is upward, b is downward. So, v cross b is in this direction. So, when a current is flowing through a wire in the upward direction, then the magnetic field has a force on the wire which is towards the left as drawn here. Now, I want to calculate what is the net force acting on this wire because of this charge motion. We know that the magnetic force is equal to q v cross b. B is the velocity of the charged particle, q is the charge of the particle, and b is the magnetic field. Now, as I mentioned, I will assume that these are positive charges moving up in the wire constituting a current. So, let me assume that the drift velocity of the charges is equal to b. So, the force on each charge, the magnitude of the force is q times v times b. It is in this direction, it is in the direction shown here. The magnitude is q times v by b because velocity vector is perpendicular to the magnetic field direction. So, v cross b is nothing but v times b. Now, that is the force on one charge. So, I need to calculate the force on the entire wire, which has not just one charge, but a large number of charges. So, for this let me assume that the charge density which is charge per unit volume I need to calculate the charge density, how many charges are there in this thing. So, let me assume that the charge density, that means the number of charges per unit volume, the number of charges will be equal to, let me assume n. So, there are n charges per unit volume in the wire which are flowing upward in the direction of the current. So, in this volume, what is the volume of the wire? Volume is equal to the cross area times the cross sectional area is A and length of the wire is L. So, the volume of this wire is A times L. So, the number of charges present in the wire of length L is equal to n times A times L. A times L is the volume, n is the number of charges per unit volume. So, the total number of charges is this. So, total charge is equal to n A L times Q. Each of the charge has a magnitude Q. So, the total charge of this volume is n A L into Q. So, the force is acting, magnetic force is acting on all these charges. So, the total force on the length L will be equal to n A L Q, which is the charge, times V times B. The number of charges, each charge is acted upon by force charge times Q B. So, here there are Q B, there are so many charges present. So, the total force on the charge on the wire of length L is n A L Q into V B. Now, I want to relate this to the current flowing through the wire. So, now what is the current? To calculate an expression for the current, let me take a wire, the same wire of cross sectional area A of length V. What is V? V is the velocity, drift velocity of the charges. So, I take a wire of the same cross section A and of length V. Now, because V represents the velocity of the charges in this direction, remember all the charges contained in this volume will cross this area in a unit time. So, as the charges are moving up, all the charges, because this distance is V, the charges move a distance V in a unit time. So, in a unit time this surface will come to this surface. So, all the charges present within this volume would have crossed this surface in a unit time. So, this is the length V, all charges contained in the length V will have crossed the upper surface in a unit time. So, the current is nothing but current I is equal to the charge flowing per unit time, which is equal to, so what is the volume of this? A times V is the volume, the number density is n. So, n times A times V is the number of charges into Q. A times V is the volume, n is the number of charges per unit volume. So, the number of charges is this, and so the total charge is n A V into Q, and that must be the current. So, that is the current flowing through the wire. So, I can replace n A V times Q by current I, and I get the force which is equal to I times L times B. So, here n A into Q V, n A Q V is I, remaining I have L and B. So, the force is nothing but current multiplied by length of the wire multiplied by the magnetic field. So, that is the force acting on the wire, and so if we draw the wire again here. So, this is the wire carrying a current I, and the magnetic field is pointing into the page of the wire, to the page here, and these are positive charges moving up. So, the net force is in this direction, V cross B. Now, this is a case where the current is flowing perpendicular to the magnetic field, but this may not be always true. I can have a current carrying conductor which is not oriented perpendicular to the magnetic field, but at some angle to the magnetic field. So, I want to calculate what is the force on a wire which is carrying a current, but that current is not flowing perpendicular to the magnetic field. So, let me draw a figure here. So, this is a wire is oriented like this. This is the current carrying wire. Let me draw the axes. This is z axis, let me assume, this is x axis, and the current is going like this. And let me assume that the magnetic field is oriented like this. So, now you see I have an angle between the current carrying conductor wire and the magnetic field, and that angle is not 90 degrees, it is some arbitrary angle phi. The earlier example we had considered was a situation when phi was 90 degrees. So, now I want to calculate what is the force on this. So, what is the magnetic field? Magnetic field B vector is equal to B times magnitude times k cap. Magnetic field is oriented along the direction. What is the velocity vector of these charges? Velocity is moving like this. So, it has both x component and z component. So, x component is v sin phi, and so v sin phi is the x component and z component is v cos phi. So, the velocity of the charged particle is given by v sin phi I cap plus v cos phi k cap, and where v is the magnitude of the velocity and the magnetic field is b times k. So, force on every charge, force on one charge q v cross b, which is equal to q b sin phi I cap plus v cos phi k cap cross b k cap, which is equal to q v sin phi I cap cross k cap cross k cap is 0, and I cap cross k cap is minus j cap. So, the minus q v b sin phi j cap. So, remember in this figure y axis is pointing up in the pitch because of the right handed system, x, y, z, and the force is in the downward direction, as you can see here, v cross b must be downward. So, it is minus j cap direction. So, that is the force on each and every individual charge passing through the wire, and I can relate this to the current, and by calculating again the total charge in a length L must be equal to NAL times Q as before. So, the total force on length L will be equal to minus NALQ, that is the charge, into V into B sin phi j cap. And I know the current as before, I is equal to, we had done before, current is equal to N times A times B times Q, that is the current flowing through this. So, this is nothing but this force is equal to total force on length L is equal to minus B into L sin phi j cap, which is nothing but I L cross B, where L is a vector which is actually L sin phi I cap plus L cos phi k cap. L vector is this vector in this direction, it has a x component L sin phi I cap, and a z component which is L cos phi, and this force is nothing but I L cross B. So, if you have a wire carrying a current I of length L placed in the magnetic field given by B vector, the total force acting on that length of wire, straight length of wire, is I L cross B. This is a uniform magnetic field, and I have a force which is I L cross B. So, I can actually, if I do not have a straight wire and if I have an infinitesimal length, force on an infinitesimal length dl of wire, current carrying wire, is equal to I dl cross B, and this is equal to nothing but a force which I call dF. So, if I have a wire of a certain shape, I can consider small elements of dl vector along the wire, and each of these dl vector has a force acting on it which is given by I dl cross B, and from this I can calculate the net force acting on the total wire of any shape, etc., by integrating over all the forces acting on each and every element of wire. Now, I have assumed here that the current consists of positive charges flowing up, but actually the current consists of electrons flowing down. So, let me see what happens because of electrons going down. We saw that if the positive charge is going up, magnetic field is pointing inward, the force is V cross B, which is in this direction. Instead of this, if I have electrons going downwards constituting the same current, V cross B is now this direction, but because the charges are negative, the force is essentially back in the same direction. So, independent of whether I consider positive charges moving up or negative charges moving down, the net force acting on the wire is essentially given by this direction here, which is F is equal to I dl cross B on the current carrying conductors of infinitesimal length dl. So, I can use this to calculate the forces on various situations when I have current carrying conductors placed in magnetic fields. Now, before we go to a more general situation, I want to find out what is the force between two current carrying conductors. So, let me take force between two current carrying conductors. So, let me take two straight conductors. This is carrying current I 1, this is carrying current I 2. For the moment I am assuming that the currents are going in the upward direction parallel. Let me assume the distance is d. Now, there are two wires carrying current in the upward direction, parallel currents, and I want to find out what is the force between these two wires. Now, why there will be force? Remember, this current carrying conductor produces a magnetic field at the position of this wire. So, current is moving up. So, what is the direction of the magnetic field? Magnetic field on the second wire is pointing downwards, and we know the magnitude of the magnetic field. We will actually calculate the total force it is. So, current is going up, this wire is producing magnetic field in this wire, and so we have just now seen that if the current is going up and the magnetic field is pointing down, there is a force in this direction. So, this particular current produces a magnetic field on this wire, which then exerts a force on this wire towards the first wire. What happens to the first wire? This second wire I 2 also produces a magnetic field in the position of the first wire. What is the direction of the magnetic field? Because the current is going up here, the magnetic field is pointing towards me. Remember the right hand rule? A current going up produces a magnetic field like this. So, on this side of the wire the magnetic field is going downwards, but on this side of the wire the magnetic field is coming above the page. Current going up, magnetic field pointing up. So, what is the force? V cross B, the force is like this. So, this wire carrying current I 1 produces a magnetic field at the position of the wire carrying current I 2 and exerts a force towards the first wire. The second wire produces a magnetic field in the position of the first wire, and the force on the first wire is towards the second wire. So, it is just like two charges. these two current carrying conductors will attract each other when the currents are parallel. So, I want to calculate what is the force of attraction between these two. So, remember to calculate the force. So, let me calculate the force on wire 2 due to wire 1. So, this let me call this 1 and let me call this 2. So, now for that I need to know the magnetic field here, I know the current and I know the length of the wire. So, let me take a length L. So, what is the magnetic field produced by I1 at this point? So, B1 which is equal to, we have already seen this before, mu naught I1 by 2 pi times d. This distance is d as I have written here. So, mu naught I1 by d and that is going into the page. So, this is the magnetic field produced by this wire on this second wire, and so the force F21, force on wire 2 because of wire 1 is I2, and because the force is because the current is carrying current is perpendicular to the direction of the magnetic field, the force is in this direction. So, I2 into L into magnetic field, which is mu naught I1 by 2 pi d. So, the force is nothing but mu naught I1 I2 by 2 pi d into L. So, length L of the wire has a force F21 towards the first wire, which is mu naught I1 I2 by 2 pi d into L. So, I can write the force per unit length. Force on wire 2 per unit length F21 is equal to mu naught I1 . So, that is the force on wire 2 because of wire 1. Now, what is the force on wire 1 because of wire 2? For this I need to know the magnetic field because of I2 at this plane and knowing the length L here. So, if I have a length L again here, I can calculate. So, B2, which is the magnetic field produced by wire 2 at the position of wire 1, is equal to mu naught I2 by 2 pi d, and the force on wire 1 will be F12, which is equal to current into length into magnetic field, which is mu naught I2 by 2 pi d, which is equal to mu naught I1 I2 by 2 pi d into length. So, force per unit length of wire 1 is equal to mu naught I1 I2 by 2 pi d, the same force as the F21. So, this wire attracts this wire with a certain force F21, this wire attracts this wire by the force F12, which is equal to F21, and so the two wires get attracted to each other. So, this is nothing but essentially a description of Newton's law, that you have this particular wire attracts this wire by a force F21, this wire attracts this wire by a force F12, and F12 is equal to F21 and they are oppositely directed. So, both get attracted to each other, and that is the force of attraction between two wires which are carrying parallel currents. Now, if the currents were anti-parallel, so if the two wires were carrying wires in two opposite directions. So, if this was I1 and this is I2 here. Now, I1 produces again a magnetic field pointing away from the paper here, and this particular current is now going downwards. So, you can see the force on this will be in this direction. This wire produces a magnetic field which is going into the page here. You can use right hand rule again, and you can see the force on this is now again V cross B is in this direction. So, the forces are now repulsive, and so what we find is parallel currents attract each other anti-parallel currents repel each other. So, parallel currents attract each other, anti-parallel currents repel each other. So, let me consider an example. So, let me assume a current I1 is equal to I2, equal currents of 5 amperes flowing through 2 wires, and let me take a separation d of 1 centimeter, which is 10 to the minus 2 meter. So, the force of attraction will be equal to mu naught I1 I2 by 2 pi d, which is equal to 4 pi 10 to the minus 7 into 5 divided by 2 pi into 10 to the minus 2, which is equal to 5 into 10 to the minus 4 newtons per meter. So, the force of attraction between these two parallel currents will be 0.5 millinewtons per meter, and if the currents were opposite directed, the same force will be a repulsive force between the two currents. So, what we see is currents constitute charges moving in wires, and these charges moving, when they are placed in a magnetic field, are there is a magnetic force force exerted on these charges, and so current carrying conductors also have forces exerted on them by magnetic fields, and we have been able to calculate what is the magnetic field on a current carrying conductor. And if you take an infinitesimal length dl carrying a current I, the force is nothing but I dl cross B. So, if you are given a current carrying circuit of an arbitrary shape, you can break this up into small elementary lengths dl vector, calculate the force on each of these dl vectors and add them up and to calculate the total force. Now, I want to have an application of this to the calculation of a torque on a current carrying loop. Torque on a current carrying loop placed in a uniform magnetic field. So, I have a current carrying loop placed in a uniform magnetic field, and I want to calculate the torque on this. So, for this I want to take an example of a rectangular current carrying loop of sides A and B carrying current I. A loop is placed in a magnetic field B. So, now let me draw a figure to show you the geometry of the problem. So, let me draw the axes first. So, I have the x, y, z. I assume a planar loop placed in the xy plane carrying a current like this. So, it is a planar loop of side A by B. So, let me call this side A, this is B. A rectangular loop of A cross B carrying a current I and placed in it is a planar loop and placed in the xy plane. Now, the magnetic field would have some arbitrary direction, but let me as an example here consider the magnetic field to be in the yz plane pointing at some angle like this. Now, let me call this angle phi. So, this is a planar loop like this, it is a loop placed like this in xy plane, and there is a magnetic field pointing in some direction like this, in this direction here, making an angle phi with the vertical. So, the current carrying conductor is a rectangular loop like this, current carrying a current, and the magnetic field is necessarily not perpendicular to this plane or parallel to this plane, it is some angle making an angle phi with the normal to this plane and lying in the visor plane. So, I want to calculate what is the net force acting on this current loop and what is the net torque acting on this current loop. So, for this let me write down the magnetic field of this given in this figure here. Magnetic field has a component which is along y and a component along z. So, I have B sin phi j cap plus B cos phi k cap. It has a component B sin phi along the y direction and a component B cos phi along the z direction. I am assuming the magnetic field to be lying in the yz plane. So, this magnetic field will now have a force on each of these elements, and according to the formula we have derived earlier, we can use what is the force on this element, what is the force on this element, what is the force on this element, and what is the force on this element. So, let me call this paths 1, 2, 3 and 4. So, 1 is this length here, 2 is this one, 3 is this one and 4 is this one. So, I want to calculate the forces on all these 4 current elements constituting the loop. So, let me start by force on 1, that is this force on this element. Now, for this I need to know, I know the force is I L cross B, L is the length of the wire and I is the current and B is the magnetic field. So, I need to know that current is I and I need to know what is L vector. Now, this is a line, this is a current carrying conductor pointed along the x direction. So, L vector for this will be, L vector will be simply and of length B. Look at this figure here, this length is B, point along the x direction, current is flowing along the x direction. So, L is actually nothing but B times I cap. B is the length of this vector L, this is the current carrying conductor here, length is L, the length is B here and it is flowing along the x direction. So, L vector is nothing but B I. So, force F 1 will be equal to I L cross B, which is equal to I B I cap cross, now B vector is B sin phi j cap plus B cos phi k cap, which is equal to I B B sin phi I cap cross j cap is k cap, and then I have I cap cross k cap is minus j cap. So, I B B cos phi j cap. I cap cross j cap is k cap, I cap cross k cap is minus j cap. So, that is the force F 1 acting on the current element, this part of the current loop. Now, let me calculate the force on this part of the current, which I call F 2. This is of length A and pointing in the y direction. The current is flowing in the y direction and it is of length A. So, force on 2 I want to calculate. So, for this L will be equal to A times j cap. Length is A and the current is flowing along the y direction. The current element is along the y direction. So, L vector is nothing but A times j cap. So, F 2 force is equal to again I L cross B, which is equal to I A j cap cross B sin phi j cap plus B cos phi k cap, which is equal to, now j cap cross j cap is 0, j cap cross k cap is I cap. So, I A B cos phi I cap, I A B cos phi I cap. Remember, this force has only x component. So, this must be acting like this. This force has both y and z components. So, it must be force it is acting like this. It has a positive z component and a negative y component. So, it is a force acting like this. So, I have calculated the force on this current element and on this current element. Similarly, I need to calculate the force on this element and on this element. So, let me calculate F3. So, for F3 I must write again L. Now, L for F3 is nothing but, look here in the figure, this is a current flowing in the minus x direction of length b. So, L vector will be equal to minus b times I cap, and F3 will be equal to I L cross b, which is equal to minus I b I cap cross b sin phi j cap plus b cos phi a cap, which is equal to, now I cap cross j cap is k cap. So, minus I b b sin phi k cap minus I k cap cross k cap is j cap. So, plus I b b cos phi j cap. Now, it is interesting to note that this force is exactly minus of this force. This is I b b sin phi k cap, this is minus I b b sin phi k cap, it is minus I b b cos phi j cap plus I b b cos phi j cap. So, this force is exactly opposite of this force, and that is expected because this current carrying conductor is parallel to this current carrying conductor and the current is flowing in the opposite direction. So, the force, if this force is acting on this like this, the force on this must be like this direction. Similarly, I will leave it to you to calculate force on 4. So, L vector for this will be equal to minus a j cap, and F4 will come out to be minus I a b cos phi I cap, just which is just the minus of this force. Here it was I a b cos phi I cap, here it will be minus I a b cos phi I cap. So, there are four parts to this current this circuit or this current carrying conductor, and I have calculated the forces on each of these parts. So, I can from here calculate the total force on this current carrying conductor. So, total force F1 plus F2 plus F3 plus F4, and you can see here F1 and F3 are exactly equal and opposite to each other. F1 and F3, this is F1, this is F1, this is F3, they are exactly equal and opposite to each other. Similarly, F2 and F4 are exactly equal and opposite to each other. So, F1 and F3 cancel off, F2 and F4 cancel off, and the total force is 0. So, a current carrying loop placed in a uniform magnetic field has no net force acting on the current on the loop, and the net force is 0. Now, although the net force is 0, because of these two forces there is a torque acting on this system, and we need to calculate this torque. So, let me draw the figure again here. So, I have this current carrying conductor here. So, there is a force in this direction, there is a force in this direction. So, let me look at, so this is, let me draw the plane again here, this is y, this is z, this is x. So, let me draw the figure in the yz plane to be clearer. So, this is y, this is z. So, there is a conductor here, there is a conductor here, this current is flowing here like this. So, this current is flowing towards me and this current is flowing away from me, and this force is like this and this force is like this. So, this is F1 and this is F3. Please note that F2 and F4 do not create any torque on the loop, because F2 is like this and F4 is like this. They are exactly equal and opposite and acting through the origin here. So, effectively they are parallel to the x axis and there is no net torque, but these two forces can create a torque around this. I can calculate the torque around this point O. Remember, this distance is A. So, I can calculate the torque because of these two forces. So, let me calculate the torque now. So, let me have the figure here. So, torque due to F1 about O. So, let me call this tau 1 is equal to r 1 cross f 1, and where r 1 is this vector here, this vector is r 1 cross f 1 is the force. Now, r 1 has a length a by 2 and is oriented along minus y cap direction. So, minus a by 2 j cap cross f 1 we have calculated before, f 1's expression is here. So, let me substitute the expression for f 1, I b b sin phi k cap minus I b b cos phi j cap. R 1 cross f 1, j cap cross k cap is I cap. So, this is minus I b a b by 2 sin phi I cap. J cap cross k cap is I cap, j cap cross j cap is 0. So, minus I a b b by 2 sin phi I cap, that is the torque of this force around this origin O. I can similarly calculate torque due to F 3 about O. Now, this is R 3. So, I can write tau 3 is equal to R 3 cross F 3, and R 3 has a magnitude a by 2 and directed along y. So, this is equal to a by 2 j cap cross F 3 vector. F 3 vector we have again calculated before, and F 3 vector is here. So, minus I b b sin phi k cap plus I b b cos phi j cap. J cap cross k cap is I cap, j cap cross j cap is 0. So, I get again with the minus sign here minus I a b b by 2 sin phi I cap. So, the torque due to force F 1 around this point is this, torque due to F 3 around this point is also the same, and they are same orientation. So, the total torque tau 1 plus tau 3, which is nothing but I minus I a b b sin phi I cap. Minus I a b b sin phi I cap. I want to write this as follows. So, I want to write this as I a b b sin phi into I cap is nothing but, so minus I cap is k cap cross j cap cross k cap is I cap. So, minus I cap is k cross j k. So, tau I want to write in terms of a vector like this. Now, why I am doing this, you will just become clear. So, this is my torque as calculated from the calculation of the total forces acting on the 4 components of the current element, current circuit. And so, remember we had introduced the concept of magnetic dipoles, and I had introduced what is called as a dipole moment. Is equal to current into area, and area is a vector. So, in my case look at the figure here, this is z direction, this is y direction, this is x direction, current I, this length is A, this length is B. So, now remember we had defined an area vector. Here if I use the right hand rule, this area vector has a magnitude, the area of this current loop, which is A times B, and according to right hand rule its orientation is along the z axis. So, area of this will be A B K cap and current is I. So, for this current loop M is equal to I A B K cap. M vector, that is the magnetic dipole moment of this, is nothing but I A B times K cap. Now, we already know the direction of the magnetic field. B is nothing but B sin phi J cap plus B cos phi K cap. So, let me calculate M cross B. I A B J cap cross B sin phi J cap plus B cos phi K cap. J cap cross J cap is 0 and I have I A B B just one second. Sorry, this is I A B K cap. I am sorry, this is K cap. So, K cap cross J cap is I cap. So, let me write this as B B into sin phi into K cap cross J cap. K cap, sorry, this is K cap cross J cap is there. It is not 0. K cap cross K cap is 0. So, I get I A B into B sin phi K cap cross J cap. So, let me compare this with the expression for tau we have obtained. I A B B into capital B into sin phi K cap cross J cap. So, this torque is nothing but M cross B. So, I get a torque on this current loop, tau is equal to so if I have a current loop like this, the two forces are acting like this, there is a magnetic field oriented in some direction and this will tend to, so this is x direction, this is y, this is z direction, this is y direction. The M vector is pointing up, magnetic field is pointing like this. So, M cross B gives me the direction of rotation, that is the torque, and this torque will tend to orient the dipole in such a fashion that torque finally becomes 0. So, this is the torque acted upon on this current loop having a magnetic dipole moment M, and this is very similar, if you recall our discussion in electrostatics, this is very similar to the torque on an electric dipole. Which was P cross E. The electrostatic torque on an electric dipole is P cross E. P is the electric dipole moment and E is the electric field. Here the torque is magnetic dipole moment cross the magnetic field B. It is the same similar expression and it gives you the torque on the current element. So, the torque becomes 0 when M and B become parallel. So, the magnetic field tends to align the dipoles along the direction of the magnetic field. So, that the torque becomes 0. In fact, when M is anti-parallel to B also torque is 0, but M parallel to B is a stable equilibrium position, the opposite direction is an unstable equilibrium position. So, you can work it out to show that when M and B are parallel you have a stable position, when M and B are anti-parallel you have an unstable position of equilibrium. So, this will give me a torque, and so if I have if the loop contains n turns closely wound, then the dipole moment is nothing but n times I times area times. So, the torque gets multiplied by the number of turns in the coil, and so you have a higher torque if you have more turns in the coil than if you have a single turn in the coil. So, the torque not only depends on current, it also depends on the area of the loop, it also depends on the number of turns. So, this torque is used in many electrical instruments, for example motors and generators and many other types of instruments. What I would like to study in the course here is an application to a current measuring device which is called the moving coil galvanometer. So, whenever you place a current carrying loop in a magnetic field, there is a torque acting on this. If you have uniform magnetic field, the net force is 0, but if you have but there is a torque acting on this which tries to align the magnetic dipole with the magnetic field, and this torque can be used to make instruments. So, here I want to consider what is called as a moving coil galvanometer. So, let me draw the construction. It consists of a pair of permanent magnets here. This is the north pole, this is the south pole. So, magnetic field is going from N to S, and in the center you have a coil in a wound on a soft iron core, and this coil is carrying current. So, let me the coil goes like this, a number of coils going here. So, the coil is like this, and this is connected to a spring, and which spring has a needle pointing. So, this spring is fixed. If you try to twist this, the spring gives a restoring force and tries to bring it back. So, restoring force is created by the spring, and remember there is a magnetic field because of the shape of these pole pieces here. The magnetic field is pointing like this from the north pole to the south pole. So, this is one the directional magnetic field is from this point to this point. So, you have almost a radial magnetic field. So, now let us see what happens when I pass a current through this coil. When a current passes through this coil, these two are current carrying conductors placed in a magnetic field. So, torque acts on this current carrying coil, trying to rotate this coil around this axis. So, when the current is acted upon by a force and the coil turns to rotate, the spring provides it a restoring force. So, if you pass a certain current of a certain magnitude, the coil will rotate and stop, because at that point the torque provided by the magnetic field is balanced by the torque provided by the restoring spring. So, the needle will rotate, and that will be an indication of the current passing through the coil. If you change the current, the torque changes and the deflection of the needle will change. So, the deflection of the needle becomes proportional to the current passing through the coil, and so the deflection of the needle is an indication of the current that is passing through the coil. So, you can get an indication of the current passing through the coil by simply looking at the deflection of this needle, and that is called a moving coil galvanometer. And so, let me calculate what is the deflection of this needle. So, the torque due to current I. So, let me call this tau current, which is equal to number of loops I into A into area into magnetic field. A is the area of the current loop, I is the current propagating through the loop, there are n loops, and B is the magnetic field. So, A is area of loop, n number of loops, and I is the current, and B is the magnetic field. So, this will produce a deflection, and the restoring force provided by the spring will be proportional to the displacement, angular displacement, where k is the spring constant. So, I will stop here. What we will look at is the next class, how to make this galvanometer into an ammeter, which is an instrument to measure current propagating through a circuit, or convert it to a voltmeter to measure potential differences across terminals in a circuit. So, this moving coil galvanometer is a very interesting example of using the torque because of the magnetic field in measuring currents.